So, as you sort of hinted through our discussion so far, inflation was introduced, it solves these fine-tuning issues, but you hint that it in fact requires some kind of fine-tuning of its own. What do you mean by that?
Good. So the question of whether inflation requires fine-tuning, that's an issue where people in the field have very different views. So there are people who claim that inflation has now been established beyond any reasonable doubt on the basis of the Planck microwave background results. And then there are people who claim that on the basis of these Planck microwave background results, inflation has now been shown to be completely unpredictive. And you see, in terms of the lack of eloquence, I was able to formulate the second part. You probably see where I stand. So I hinted already that in 1981, 82, experts were immediately able to make predictions for anisotropies in the microwave background that would follow from this wild idea of inflation. So this was 20 years before the precision measurements. So what was predicted is a roughly scale-invariant spectrum of cosmological fluctuations, which leads to microwave anisotropies which have an angular power spectrum which at large angular scales is roughly flat. And then the spectrum is not totally scale invariant, but it has a slight red tilt, which means that there's slightly less power on short wavelengths than on large wavelengths. So these are the predictions that were made in the early 80s. In fact, they were first made in a very nice paper by Mukhanov and Chibisov in 1981. So a paper which was also written behind the Iron Curtain and which people like myself in the West found out about only later. So predictions. So one of the criticisms that some people raise against inflation now is that inflation is not predictive. And I strongly disagree with that claim. I think if you just look at the history, inflation was predictive. It predicted this roughly scale-invariant spectrum of fluctuations. It predicted a small red tilt. It predicted that the fluctuations would be roughly Gaussian. And it predicted that the perturbations would be roughly adiabatic. And in fact, this idea of inflation makes further predictions which have not yet been verified. It predicts a roughly scale-invariant spectrum of gravitational waves, and we are looking for gravitational waves. We still haven't found the stochastic background of gravitational waves, although now that we've found gravitational waves, in terms of direct experiments, we are on the way to do gravitational wave astronomy. So the future is bright. And inflation also predicts quite clearly that the gravitational wave spectrum will have a slight red tilt. Okay, so I think, in my mind, inflation is clearly predictive. Now, you're actually asking about fine-tuning. So fine-tuning has several aspects. Do you need to fine-tune particle physics to get inflation? That's one aspect of fine-tuning. The other aspect of fine-tuning is, do you need to tune inflationary models to get agreement with the observations? Those are two very different aspects of fine-tuning. And again, my answer would be yes to the first issue of fine-tuning, but no to the second issue of fine-tuning. So once you have an inflationary model, then although you might not predict the amplitude of the spectrum of perturbations, you have all the other things. So that's quite good predictive power. So if you have a model, you typically have parameters in the model. And if you tune one parameter, and with that tuning of one parameter, you then can fit many data points, I think that's success. So in that sense, even though you need to fit one parameter, I think that I wouldn't object to people saying that inflation is predictive. Now the other issue is, do you need to fine-tune the particle physics models in order to get inflation? And I actually think that the answer is yes. You do need to fine-tune particle physics models in order to get inflation.
So, I mean, particularly you've talked about these scalar field models, which, you have this scalar field which lives on some potential, and inflation happens during some slow roll down this potential, let's say. And you say that you need to specifically, say, choose a potential which allows agreement with observation, allows for inflation to happen.
Yes.
So, yeah. And so, if one chooses the most simple models, the quadratic potential models, these are the harmonic oscillators that we seem to employ to do the role of almost every particle in physics. This doesn't give agreement with observations. It gives the wrong value of the scalar to tensor ratio.
Okay, so in this particular simple model, which is like a harmonic oscillator, you have one parameter, which is the mass. And you're right that with that one parameter, you can't quite fit the observed data. So you have a little bit of trouble matching the deviation from scale invariance with the lack of observed gravitational wave. Slight. It's a slight disagreement, but with some significance. And I'm not a statistician. So in fact, I'm a pencil and paper theorist. And I'm not that worried about that. Let's look at the historical development of inflation. Let's take Stravinsky's model of inflation. That is perfectly okay. So I have a friend who's a very vocal defender of inflation, Slava Mukhanov, who's the person who first calculated the density perturbations. He would give up on inflation if one of the three simplest models of inflation doesn't work. Namely, this model that you mentioned, Stravinsky, and maybe he would also allow a model in which the potential just has a quartic term. And two of these three are still in business, so Slava Mukhanov does not have to abandon inflation. In fact, he can successfully claim these predictions. Now, I would like to see this potential and the field that gives this potential. I would like this to arise from some fundamental physics that is well motivated. And for me, this is a problem. I don't see a scalar field with this type of potential emerging naturally from some ultraviolet complete theory of physics. For example, superstring theory. So I will not, if you just have to introduce a scalar field out of the hat, with a potential chosen out of the hat, then this would not be completely satisfactory. You would then have a very successful toy model, but it's not a theory. So again, a toy model is predictive, but it's not yet a theory, and eventually we'll want a theory.
So would you be happy with the recent models that Linde has been proposing involving these, I think, T models or alpha attractor models?
No, I'm not satisfied with those because those don't come from an ultraviolet complete theory. So I would be happy if you could start from an ultraviolet complete theory, such as superstring theory. And by the way, superstring theory has many candidate fields that are scalar fields. I would like to see someone show that the potential for such a scalar field has the right properties over the right range of field values to allow for an inflationary model. And I don't think someone has shown this beyond doubt.
Well, certainly.
Not everyone agrees with the statement I just made.
Yeah,
and some people don't care. Some people are happy with toy models.
Well, I mean, this actually raises the question then of, you want this to descend from this sort of more complete theory of physics. But if one can show that inflation is a sort of a ubiquitous event within a large range of theories of physics, would you not then have confidence that whatever our ultraviolet completion is, it will probably have a field that will cause inflation?
Sure, if you could show that inflation emerges in a ubiquitous way from many approaches to fundamental physics, I would be happy. Now we come to the question of fine-tuning of initial conditions to get inflation. And this is an issue which people have worked on for a while, and in particular there was a lot of work in approximately 1990, and I was involved in that. And we've shown that if you want to get inflation from the top of a Mexican hat potential, going back to the old idea, that then you need fine-tuning of initial conditions. On the other hand, if you get inflation from large field values, then this is an attractor in initial condition space. So large field inflation looks natural from the point of view of initial conditions, no fine-tuning, good. So I would like to see large fields, and by large fields I mean field values bigger than a Planck mass. I would like to see these large field values and potentials for these large field values emerging from a consistent particle physics model. And that's where the problem is. It has not been shown that quantum gravity corrections, string corrections, are under control. So let's go back to Starobinsky's model of inflation. It's based on high derivative corrections to the Einstein action. These high derivative corrections can be cast as a scalar field, as a new scalar field. And Starobinsky inflation uses values of a scalar field which are large compared to the Planck mass, but the high derivative gravity corrections are not under control for the field values which Starobinsky inflation uses. And for me, this is the problem right now for inflationary model building.
So when we talked about initial conditions, you're particularly interested in the field values and the initial parameters on phase space, let's say, which would lead to an inflationary solution.
In this multidimensional phase space,
yes,
which includes inhomogeneities, anisotropies, even gravitational inhomogeneities.
Right.
So all kinds. So it's a huge dimensional phase space. It's not only the phase space of the homogeneous motion.
Mm-hmm. So one of the big sort of challenges that has been sort of thrown at inflation recently is that inhomogeneities or anisotropies that are large before inflation would start seem to spoil this inflationary behavior.
Yeah, that's indeed an objection, which is in a paper of Ijas, Steinhardt, and Loeb, which got quite a bit of attention. Unfortunately, this is wrong, because large field inflation is safe against anisotropies and inhomogeneities, specifically inhomogeneities, as long as the inhomogeneities are not too large. And this we showed back in 1990 in a series of papers. Now, technically what we showed is that the homogeneous inflationary trajectory is a local attractor in initial condition space. You can start with energy density, which is completely dominated by inhomogeneities, and you still get inflation as long as there is some power in the homogeneous mode, because inhomogeneities are redshifted even before inflation, whereas the homogeneous mode remains. Now, if you have too wild inhomogeneous initial conditions, then indeed you won't get inflation. So at the technical level, the statement is that large-scale inflation is a local attractor in initial condition space, but the attractor basin is fairly large. And I think this is good. I'm not going to argue against inflation on this basis. Because you see, if you want to argue against inflation on this basis, you have to have alternatives. And you have to show that alternatives are better. Now you see, I do work a lot on alternatives to inflation, because since I'm worried about the conceptual problems of inflation, I'm worried about the fact that we don't have a consistent embedding of inflation into the string theory. I think it's worthwhile looking at alternatives. But can I really point out models, alternative models to inflation which do better? That's a different question. And I pause here.